Oh yeah, we're looking at the cop and the speeder problem, a classic physics problem. Number 2.36 in your workbook. And in that problem, let me just get this. I'm not stressed out. In this problem, we can see the speeder. If you want to look this up, it's on page 41 in the workbook. The speeder is moving with constant speed v. The cop is going to accelerate from rest. And we're going to start with these two main questions here. And then maybe after we figure this out, we could talk about how this looks graphically as well and how you can interpret that. All right. So in this case, we have a speeder moving with constant speed. Hopefully, that tells you if something's moving with constant speed in a straight line, acceleration should equal 0. Immediately, I see kind of some problems here. We've got two different objects. Maybe what I'll do is I'll label this object number 1 and this object number 2. So we're basically going to do our two-stage problems. So in this case, I could say A of 1 is equal to 0. And I could say velocity of 1 is equal to v. Now, in this case, the cop is going to accelerate from rest. So that's going to be a changing velocity, but I could say that A2 is equal to A and V2 initial is 0, right? It's accelerating from rest, so that tells me the initial velocity is 0. I hope you can guess what I'm going to do with this. It's a two-part problem. So it's basically a two-stage problem, but one stage is the snail only, and the second stage is the cop only. So now we have two questions. And I just want to point out something important here. The max separation distance and how far from the origin will the cop overtake the speeder? Now, these two questions are probably useful to, I want you to think about it this way. Initially, the cop is at rest, and the speeder is going to be trucking along with some speed v. The speeder is going to first get ahead of the cop, and then the cop is going to keep speeding up. Eventually, the cop's going to be going so fast that the cop starts closing the gap. And I guess, you know what I might do is I might show you a simulation here in advance with some numbers, and we'll come back to this. So maybe this will make some sense out of what's going on if I can get the right. Let me edit this program and run it. Okay, and I'll share the screen. All right, now I realize this might look a little bit small, but I'm going to try and put a lot of information here. So I'm going to run the simulation when I click on it, and here's what happens. We can see a lot of crazy stuff going on. Now, I'm going to run that again just so you can watch it. And maybe what I'll do is I'll set the sim speed a little bit slower. Let's set the sim speed to 1. I'm going to run this again so I have time to talk. In this case, we see that the speeder quickly pulls ahead, but somewhere right about right now, the cop is starting to catch up, and we see the cop's velocity is starting to get so big that it's closing the gap, and then eventually somewhere way the heck out here, it looks like they catch up to each other. So now we see, I hope you could see the use of the graphs now. This graph shows us they catch up. So this is the point in time when they catch up with this set of numbers. And now this is the special time here where you get max separation. I'm just going to say max sep. All right. Now notice on here, if you look, the gap between the two curves is biggest at about 4 seconds. And in this simulation, I don't know if you notice down here, the results that I got for these particular sets of numbers, if I use these particular numbers here, right, you might be saying, well, how did you make this simulation? I solved the problem behind me algebraically and then punched it into the code so I could type in any numbers I want. This is really our first problem where it can start to put together everything that we've learned through the whole semester. But here is something interesting. I want to point out X2 final equals X1 final when they catch up. If you're talking about max separation, we see that V2 final equals V1 final. At the moment their velocities are equal, that's when they have maximum separation. Any less velocity from the cop, the speeder is still gaining. Any more velocity from the cop is closing the gap. And then I made a comment here. This simulation was made using a small time step. It turns out if you want this to be more accurate, you have to use a smaller time step. So there's some rounding errors here. So if you're wondering why this is rounding error, like, shouldn't this be 40 and 160? I think it is, but I don't know. We could use a smaller time step, but then the simulation takes more time to run. I'll put a link to this simulation in the comments of this video, but let's go back to this. I hope you see the use of graphs now, right? This is a lot more, or maybe the simulation, right? It's a lot easier to understand this problem if you can visualize it and plot the motion, and you can just see screaming out of the plots these obvious spots to look for. So that's why I spent some time on learning how to plot things. You can really understand problems deeper. Why are we going to do this problem algebraically? I would never have been able to create that code if I hadn't done the problem algebraically and then started punching in numbers. So yeah, that's all right. I don't know. I hope that's kind of slightly interesting to you. So in this case, let's just pick the max separation condition here. So let's do part A. If I'm doing part A, I'm going to do two sets of knowns. So I'm going to say delta X1, V1 initial, V1 final, acceleration 1, time 1. All right. In this case, we're going to max separation distance. So I'm doing part A. Let's see, I don't know this, but the speed is V for both of those, and the acceleration is 0. We're going with constant speed in a straight line. Constant speed in a straight line, acceleration is 0. Time is unknown. All right. Let's do object 2. Delta X2, V2 initial, V2 final, A2, and T2. Now, wait a second. This is kind of interesting. In this particular problem, the two objects are driving for the same amount of time. So what I might do to make this a little bit easier, I don't know the time, but I could call it T. And what that does is it helps me reduce the number of unknowns in my equations. I don't have to deal with T1 and T2. They're all the same time T. Okay, and now I have to use this information. Max separation implies they have the same velocity at the end of the problem. So this has got to be a V. It starts from rest, so this was a 0. I don't know the distance, but I do know A2 is A, I believe. So notice we get a lot of information here. And in this case, we could then start writing equations. So if I write the final 1, well, you know what? There's not much to get out of this one. Let's start with number 2. You might, if you're not sure, you can start writing equations blindly and then just checking. But in the interest of time and making this video short, I'm going to start with this. V2 final equals V2 initial plus AT for 2. And I don't need a subscript 2 because they have the same time. So just to emphasize that, I'll put that in black. So that's the one that's common to both of them. Okay, that's why I don't need a subscript. It's the same time for both. Well, if I plug in the zeros, I can see that, I can see that V equals A T, or T is equal to V over A. Now that now keep in mind, V and A are givens. So this is something that's known. This is known. This is known. This is known. The idea here is V is a known quantity in the problem statement. It was one of the letters that we're given to play with. A is one of the letters we were given to play with. So now time, in theory, could be figured out. If you tell me what V and A to use, I'll give you the time. That's how my code works. Next, I could take this and stick this into another equation here. We could say delta x1 equals V1 initial time plus A1 1/2 A1 T squared. Again, the time doesn't need a subscript. And I chose this position here to get the position of 1. Keep in mind, they both started at x initial equals 0. If we choose to say this, so in this case, because everything's moving to the right, strictly speaking, this should be a displacement. But if the initial position is 0, then delta x should correspond to distance in this one case. All right, we're pulling together everything from this whole chapter. Now, in this case, we know A1 is 0. That drops that out. My time is V over A. So notice take a second to buy into that. Delta x1 is using V1 initial is V. So if I plug in a V and a V over A, I get V squared over A. I could then do delta x2. Maybe I'll put this time in black just because I didn't do a perfect job color coding. I apologize. These should have been in red, right? I'm a bad person. I'll put a red box around. How about that? So that's using the numbers from that case. These are using the numbers. Oops. We're going to use the numbers from the blue case. So it's basically bookkeeping, keeping track. And you might be saying, man, why do all this writing? Why don't I just figure this out in my head? As the problems get harder and harder, it helps to have things that are neatly labeled, right? So when I plug this into here, let's see, now my V initial 2, remember the order of the subscripts doesn't matter. It's just telling you it's 2 and initial. This is initial and 2. So that's 0. This term drops out. And I see that delta x2 is equal to, what is that? 1/2 times A times the time was V over A, and then I got to square it. So out of all this, I think we get, let's see, one of the A's will cancel. We'll still have the 2. It should be 1/2 V squared over A. Or you could say V squared over 2A. Now, in this particular case, we're not done yet. I want the maximum separation distance. Well, that distance should be the bigger one minus the smaller one. It just so happens when you do this, in this one case, the bigger one minus the smaller one, boy, where am I going to put this? I'm going to put it right here. Max sep equals, in this case, it would be the bigger one, delta x1, minus the smaller one, delta x2. Is that still on the screen? Just barely. Which in this particular case, maximum separation happens to be, geez, I need some more room here. Try to squeeze this all in so I can use the other board for part B. In this case, out of all that information, the maximum separation is equal to, what did we say it was? V squared over A minus 1/2 of V squared over A, which that's going to happen to equal, in this one case, 1/2 V squared over A. And again, you could just write that as V squared over 2A. That probably looks prettier. So let's do that. All right. So that's my maximum separation distance. That is the answer to part A. Well, now we can go back and do the other problem, and where this gets interesting I need to go to the other whiteboard. Let's go to here. Come on. Today. There it goes. Part B. It was something about how far to go before the cop overtakes. Something like that. So I'm going to redraw a picture and start over. Okay, this is x equals 0. And you know what? Let me start over here. I'm going to have object 1, which is the speeder. I'm going to have object 2, which is the cop. They're both going to start at this point, which we're calling x equals 0. So the initial value of x is 0 for both of them. And eventually, the speeder is moving with speed v. And the speeder is going to keep moving at some speed v. Now, what's going to happen here is the cop cannot catch up unless they're going faster. We know from the previous work that at some point in between, there's some max separation when they have the same speed. I hope it's obvious that the cop cannot have the same speed. The cop's going to have to be going faster, and I don't know how fast that is. Right? But the cop has to be going faster, otherwise they'd never catch up. Okay? And we're claiming the cop catches up. We do know the following sets of garbage here. We know that delta x1 is unknown. Velocity 1 initial equals velocity 1 final equals v. The acceleration of 1 is 0. And I only have one time because they both have the same time. Time is an unknown. For number 2, I don't know. You might be saying, wait, didn't we just figure these out? No, we figured out the max separation delta x is this is a new problem. They have a different x value now. We can't use the old x values. So now I do know that V2 initial equals 0. V2 final equals, I don't know. It can't be V. It's got to be faster. But I do know its acceleration is still a. And I do know we could use the same time, but I don't know what it is. All right, so there's our list of knowns and unknowns. Next, we could plug in some equations here. Well, in this case, last time what we did, I don't know if you noticed that, was we tried to figure out the time to catch up. This one's a little bit different. Previously, our constraint was that they have the same velocity. Now we know they have the same delta x. Even though I don't know what it is, check out this move. I could say the two delta x equations are equal. I don't know what they are, but I do know that delta x1 should equal delta x2. Otherwise, the cop wouldn't be catching up. So now I'm going to write an equation for delta x1, which for this one is just vt. You might be saying, where's the 1/2 at squared? Well, okay, let's put it in there and then set it to 0, if that's right. All right, and this is initial. Well, in this case, the acceleration goes to 0. V initial is just v, so that's going to be that. On the other side, we have 1/2 acceleration 2 times squared plus v initial 2 times t. This is 0. The time is the same for both. So we see in the previous one, we set the velocities equal and we were able to figure out something about the time. Here we're setting the positions equal and we're learning about a different time. Remember, this is a different problem. We do not have the same delta x's. We do not have the same t's. We have to solve for them again. All right, so in this case, I get vt equals 1/2 at squared. You might be saying, oh, I could just divide by t on each side. True. Notice one time they have the same delta x will be t equals 0. Well, when they're at the starting point, right? Yeah, that's true at the starting point, but that's when the speeder is overtaking the cop, not the cop overtaking the speeder. So I'm going to divide both sides by t, and I don't have to worry about the divide by 0 error. because we know that's the initial point in the problem. Out of all this, 2v equals what? AT? Making sure I don't screw that up. I'm gonna cross multiply here, I'm gonna divide, whoops, oh, look at that. So the time is twice as long. In our previous problem, the time to get max separation was V over A. The time to catch up is evidently this time. And so at this point, now that I know the time, I can pick either one of these two equations to figure it out. Why not pick the easier one? All I'm doing is I've taken this equation and sticking in that V1 initial is V, and out of all this, we get this is the distance traveled by one. Now keep in mind, that must be the distance also traveled by the cop because the cop caught up. Okay, so I hope this makes some sense to you. And I hope this was kind of an interesting way to tie together everything we've been doing. One last comment, why does every physics teacher always do this problem? Turns out this is foreshadowing the next chapter, 2D motion. If I could just pretend for a moment that this would be the speeder is representing the motion of a ball moving horizontally, and the cop could be like the ball's vertical motion. We know that when you throw a ball horizontally, gravity pulls it up and down, so you get an acceleration in the vertical component, but not in the horizontal. More on that in the next chapter. But the mathematics of this is very similar to the mathematics in the next chapter. All right, that was a big problem. I'm going to run the simulation one more time. You can stop the video if you want. Let's go back to there and see it in case you want to tie this all together. All right, so here it is. The idea is we see that the speeder is getting ahead. Somewhere right about 4 seconds, we should see the cop catches up. The cop has the same velocity and starts closing the gap. And then somewhere close to 8 seconds, the cop will finally catch up to them. And so you can see the answers down here at the bottom. Hopefully this is showing up on Zoom pretty well. I hope not. I hope so. And if not, I'll put a link to the simulation so you can run it in there. And then again, notice there's some rounding error because I used we expect some errors somewhere around, I don't know. That's what gives rise to these rounding errors. I'm going to leave it at that. Hopefully that makes some sense.